Uh, from GPS package 12.5. So in this question, right, what I'm asking for you to do, right, is draw and label an energy diagram that shows the potential energy of the molecules in a reaction change over the course of the following elementary reaction, right? So what the reaction is that you have methanol reacting with iodide to form methyl iodide and hydroxide ion. And so I give you two pieces of information. One, I give you the delta G of the reaction, right? So I give you the Gibbs free energy, and then I also give you the delta G double dagger, right? So I give you the free energy of the activation energy, right? So that's two pieces of information that we have. And so what I'm looking for, right, in this case, is just simply a plot, right, where I have delta G in the y-axis, right? So that's our energy in this case, and then we have reaction progress here at the bottom. Now, typically, right, what you have is you're going to have a starting point and you have an end point. And then, when you do the reaction progress, when you're doing kinetics, you always have then the hump, right, showing how much energy is required to go over. So what I gave you right here was, the energies of those reactions. And so that should be able to tell you, give you two pieces of information. One is the information of what the energy difference is between, the starting material and the final product. And it should also give you what the energy is, energy difference is between the starting material and the top of that hump, right, of the kinetics. And so, an important thing to look at, right, is if we're looking at the delta G of the reaction, it's not negative, right? It's not the starting materials are actually at lower energy compared to the product in this case, right? So that's a very important thing to think about, because usually when we do these kinetics things, we're always drawing it as if it was a spontaneous reaction where it's going, from one species to another one, right? But then the product is lower in energy, right? It's a spontaneous, thermodynamically spontaneous reaction in that case. That's not the case right here, right? So that's an important thing to look at, is that the delta G of the reaction is actually positive in this case. So that should tell us, right, that our starting materials, right, so the CH3 OH plus the iodide in this case should be lower in energy compared to the products, right? So in our case right here, that would then be the methyl iodide hydroxide ion in that case, right? And so you have that energy difference right here. So this is that energy difference, is that delta G of the reaction, right? So that's strictly a thermodynamic plot showing the difference between the two of them right there, right? So you have to put in, that much delta G for that reaction to happen, right? That much free energy, which should tell us, right, that it's not spontaneous, right? It's not going to go on its own in this scenario. So that's part one, right? So we're able to figure out where the starting material and the end material is in that case. The next thing, right, is to draw out what the reaction profile looks like, right? Like the kinetic energy, or sorry, the kinetics part of it, right? Which is then where we're going, and then we have that hump in this scenario, right? So you always have to have, overcome some type of energetic barrier for a reaction to happen. That barrier can be really small, can be really large, right? But it has to exist. And so in this case right here, right, that energy difference, right, is the delta G double dagger in this scenario, is going to be large, right? So it's 434 kilojoules per mole. So it's, it should be above, the products in those scenarios, right? And it should be, approximately, almost, I guess you'd say like 1.5, close to 2 times as large in this scenario, right? But that's, an approximate drawing of what's going on in this case, right? And so that's what the potential energy, change of that reaction is, both from a kinetic perspective, so you have the delta G double dagger, and then also from a thermodynamic perspective, where you have the delta G of the reaction. So that's how you do A8.